Good morning, everyone. Before today's plenary lecture, the Geochemical Society and the EAG, the European Association of Geochemistry, are pleased to welcome 5 of our partner societies as they present their annual awards. First, I would like to invite Tetsuya Yokohama, President of the Geochemical Society of Japan, to present the Geochemical Journal Award. Tetsuya.
Okay, so the Geochemical Journal Award is presented annually to the author of the most outstanding papers published in the Geochemical Journal in the previous year. The 2026 award is given to Kohei Matsuoka, Takano, Kawaguchi, Toki, and Solin for their most outstanding paper entitled Concentrations and Isotopic Ratios of Molybdenum and Tungsten in Okinawa Trough Hydrothermal Fluids, Novel Proofs for Hydrothermal Processes in the Backup Basin, published in Geochemical Journal, Volume 59, page 283. So, congratulations.
Thank you.
This is the plaque. And prize. So, Matsuoka-san, how do you feel?
It is a great honor to receive these awards, and I would like to thank for everyone at Geochemical Journals for this recognition. Thank you.
And Kohei, what is the most strong point and appealing point of your paper?
Okay. In these papers, we analyze for 2 elements, molybdenum and tungsten. It is not so major element in this in these regions, but we can we can show the possibilities of tracers about understand the complex hydrothermal process.
Okay, great, thanks. I personally work on the molybdenum and tungsten, so I'm very excited about this outcome. And also, I would like to have this time opportunity to introduce our journal, Geochemical Journal. It actually has the long history of 60 years. So this is the annual year of the volume 60. And the most exciting point is this is the open access journal, and the open access fee is just only $600, $600 US. In this situation, you guys have the big opportunity to submit your next paper to Geochemical Journal. And if you become a member of the Geochemical Society of Japan, you will get some reduction of the fee. So just consider to submit your next paper, exciting paper, to this journal. Thank you very much.
Thank you. Next, I would like to invite Fangzheng Teng to present the Sen Chun Chun Foundation Award.
Thank you, Dominic. The Shensu San Award, established by the Shensu San Foundation, recognizes an outstanding young geochemist under the age of 40, working in mainland China, Taiwan, Hong Kong, or Macau. So the 2026 Shensu San Award is presented to Professor Mang Lin in recognition of his pioneer contributions to multiple sulfur and oxygen isotope geochemistry and the transformative applications to Earth and planetary sciences. Professor Lin received his bachelor degree from Sun Yat-sen University in 2008, and he got his PhD from UC San Diego in 2018 under the supervision of Professor Mark Simmons. Okay, too many Mark. So he is, yes. He is currently a professor at the Guangzhou Institute of Geochemistry, Chinese Academy of Sciences, and also he is the director of the State K Laboratory for Deep Earth Processes and Resources. Please join me in congratulating Professor Lin on this well-deserved honor.
Thank you, Fang Zhang. Next, I would like to welcome Dorit Jacob to present the International Association of Geochemistry Early Career Award, Research Award.
Thank you, Dominique. Hello, everyone. My name is Dorit Jacob, and I'm here in my capacity as the president of the International Association of Geoanalysts. I, too, would like to thank the organizers for allowing us to present this award at this meeting. Our awardee gave a brilliant lecture on Monday morning, for those of you who have seen it. The International Association of Geoanalysts promotes the advancement of geoanalytical science and supports the professional needs of those involved in the analysis of geological and environmental materials. The IAG highly values the contributions that early career scientists make to the field. So every year, the IAG bestows the Early Career Research Award for Excellence in Analytical Geochemistry to recognize these contributions. Eligibility is limited to scientists who are currently pursuing a higher degree with a focus on geoanalysis, or to those who have completed their university education within the past 3 years. And I would like to point out we are now accepting nomination for next year. So please think of those around you and nominate your early career scientists. So Dr. Saini Samim focused her PhD on the application of high-resolution tephrochronological tools, including grain-specific laser ICP-MS, laser ablation ICPS trace element geochemistry on paleoanthropologically important volcanic ash layers in the Turkana Basin in Kenya. She has developed a new method that delivers high analytical precision of less than 5% RSDs on 27 petrogenetically important trace elements at high spatial resolution of 10 to 20 microns on thin volcanic glass shards and pumice vesicle walls. So I'm pleased to welcome Dr. Saini Samim to receive the prestigious IAG Early Career Research Award. Saini.
Thank you, Dorit. Next, I invite Isabelle Daniel to present the European Mineralogical Union Research Excellence Award.
Thank you. So, every year, the European Mineralogical Union recognizes the outstanding achievements of mid-career scientists. In 2025, our awardees, the awardees of the EMU Research Excellence Medal are Julie Cosmidis, professor at Oxford University, and Professor Alberto Vitale Broveron, professor at the University of Bologna. So I will start with Alberto. So Alberto is an outstanding petromineralogist, and he's been awarded this medal as a recognition of his action in rejuvenating the tradition of field geology and adding to that a combination of cutting-edge technologies in order to investigate subduction zones and the storage and cycling of carbon, hydrogen, and unconventional abiotic hydrocarbons. For the major impact of his numerous achievements, Alberto Vitale Brovalone is truly worthy to receive the EMU Medal for Research Excellence of the year 2025. Alberto. So the second awardee is Julie Cosmidis. So Julie, as I said, is professor at Oxford University, and she was notably able to constrain a number of biogeochemical cycles. And recently, so over the last years, she has extended our understanding of biomineralization processes and discovered novel abiotic carbon and sulfur microstructures which can be mistaken for biological remains in the fossil records. She has emerged as an international leading figure in the field of biomineralization by combining experiments in mineralogy and biochemistry and nanoscale investigation to constrain the driving force of biomineralization. And for the major impact of her numerous achievements, so Julie Cosmidis is also truly worthy to receive the EMU Research Excellence Medal 2025. Congratulations.
Merci Isabelle. Finally, we welcome Nathalie Bolfan-Casanova to present the French Mineralogical Society Merit Award.
Thank you, Dominique. So it's my pleasure to give this Merit Award 2025 to an old friend, Sylvie Demouchy. I mean, if you want to know how hydrogen diffuses in the mantle, you read her papers. If you want to know how the mantle deforms, especially olivine, you read her papers. And very soon, if you want to know how melts percolate through the mantle, you will read her papers. And she is not only a great scientist, she's also doing a lot for societies, the IMA, the French Mineralogical Society, and the EMU. Thank you, Sylvie.
Congratulations to all these award recipients. Now, it is my pleasure to introduce today's plenary speaker, Dr. Dan Frost. Dan is chair of experimental geosciences at the Bayerisches Geoinstitut of the University of Bayreuth in Germany. As an experimental petrologist, he studies the nature of the deep Earth's interior, the behavior of the mantle, and the processes that shape planetary formation. His work uses challenging high-pressure, high-temperature experiments on minerals, rocks, and melts to interpret geochemical and geophysical observation. In particular, his research focuses on redox processes in Earth's interior and their influences on the deep volatile cycle. By measuring mineral elastic properties under extreme conditions, Dan aims to constrain the composition of the Earth's deep, inaccessible layers to help geophysicists accurately interpret seismic wave velocities. Dan is the president of the European Association of Geochemistry, and in 2016, he received the Gottfried Wilhelm Leibniz Prize from the German Research Foundation. Welcome, Dan.
Thank you. Thanks very much, Dominique, and thanks all for coming. So I do high pressure and temperature experiments to try and understand the deep interiors of the Earth and other planets. But if I'm being perfectly honest, and I guess I should give this talk being perfectly honest, it's actually these people that do the experiments these days. Oh, sorry, thank you. It's actually these people that do the high pressure and temperature experiments. I'm not totally sure anymore what my role is in this, apart from standing here, in fact. So I'm going to talk about two projects that we've been involved with to try and understand the deep interior. The first, to understand the deep interior of the Earth, the lower mantle part of the Earth. And then secondly, to talk about interpreting measurements from InSight to try and understand what the core of Mars is actually made of. And what I do is I try and introduce you to some of the techniques, these high-pressure methods that we use to measure these properties. And those experiments are pretty challenging. And to be fair, they quite often go wrong. And to give you a sort of like a fair reflection of what it's like to do high-pressure experiments, the first project that I'm going to talk about actually in the end just doesn't work. So why do we want to do high pressure and temperature experiments? Well, it's really because much of the Earth is inaccessible to sampling. So if we look at the deep interior, the core and the lower mantle, they make up 70% of the Earth, but we really don't have that much idea about what their compositions are. We can make assumptions about it, but we can't be certain without making some types of measurements to investigate those areas. So I'm sure you'll hear in many talks at Goldschmidt about that there might be some uncertainty about whether the certain trace element or a certain volatile element or a certain radiogenic isotope is chondritic in the Earth. But there is really an uncertainty about what the major element compositions of the deep interior are really made out of. So I don't know. So it's a large part of the Earth. I think a more scientific way of saying that, it's the big bit of the Earth. So, and the way to investigate that is to examine seismic measurements of seismic waves traveling through the Earth. And it's important because if we want to try and understand what the composition of the Earth is made of, it's so important because it really tells us what the Earth is made from. And if we understand what the compositions of layers like the core, for example, are made from, that gives us an indication or information about how the Earth formed, the pressures and temperatures under which the Earth accreted and differentiated. So, and the way to do this is to interpret seismic observations. So when there's an earthquake, seismic waves travel through the Earth. They travel in different ways. We have S waves and P waves that travel. And by putting that information together from all the seismometers that we have around the Earth and putting all the earthquakes together, combining that with normal mode data and combining it with the moment of inertia of the Earth, we can get a model for how seismic wave velocities change throughout the Earth's interior. And that's what we do as experimentalists. We take a bulk composition, and then we try to ascertain what that composition needs to be to match the seismic wave velocities in the deep Earth. Now, when we look at the core, there's another problem. I mean, we know that the core contains light elements, and it contains quite a lot of light elements, again, that would contribute to our understanding about what the bulk Earth composition is. But there's probably too many light elements and too many possibilities to resolve that simply with knowledge of the density and the p-wave velocity alone. And that's why Mars is so important, because Mars, we think, may be a planetary embryo. It may be an example of the sorts of material that made at least a component of the Earth. And if we could investigate the interior of Mars, it might, especially the core, might give us an indication of the sorts of ingredients that went into making the Earth's core. And thankfully, thanks to InSight, thanks to the InSight lander, we now have seismic wave velocities for the interior of Mars that give us a glimpse of the Martian core. So it's really a fantastic opportunity to try and test models for what the compositions might be. So we really have the opportunity of doing the same thing for Mars as we can do for the Earth, trying to interpret seismic observations, seismic velocities into chemistry. So let me talk about the Earth's interior first of all. So it's a really big question. What is the Earth made out of in terms of its bulk composition? And if we normally think about that, we turn to chondritic meteorites, primitive meteorites, to try and understand what the Earth might be made from. But if we look at the magnesium-silicon ratios of all chondritic meteorites, what we find is that they have a much lower magnesium-silicon ratio than what we refer to as the bulk silicate Earth. And really, when we think about the bulk silicate Earth, this is really based on the composition of the upper mantle. So really, there's only two possibilities here. Either the Earth isn't made from something that seems similar to chondritic meteorites, or some of the silicon in the Earth is hidden in its deep layers. So we could still make the Earth out of chondritic meteorites, for example, if some of the silicon in these meteorites, for example, was in the Earth's core. All right, that would be the first place to look for this missing silicon. And if we put that silicon into the core, then that would raise the magnesium-silicon ratio of the remainder, and we can have the upper mantle being the more magnesium-rich upper mantle that it is in comparison to chondritic meteorites. So are there hidden layers that can explain this missing silicon in the Earth? And to do that, or to try and address this, what we want to do is look at seismic wave velocities inside the Earth. So this is the preliminary reference Earth model, or PREM. Other models are available, but in general, they do tend to kind of agree with one another, at least once you get into the main layers of the Earth's interior. So as a mineral physicist, what we want to do is try to do an experiment where we have a certain bulk composition and measure the VP and the density, for example, at high pressures and temperatures, and see if that particular bulk composition matches what we expect for that particular layer. So many experimentalists and also people doing ab initio calculations have done those types of experiments for the outer core, for example, and measured, for example, what this effect of silicon is, or the effect of oxygen would be on the properties of the outer core, and whether we can actually match those, the VP, the P wave velocity, and the density for the outer core. In a minute, I'll talk about the lower mantle, where, of course, we can match not only the density and the P wave velocity, but also the shear wave velocity. So this is results of some ab initio calculations that were done some years ago, trying to determine what the oxygen and silicon concentration of the core might be. So what they did is they found a range of solutions, which are shown here, for oxygen and silicon concentrations that would match the properties of the outer core. And what this shows is that their favorite model, for example, contains quite a low amount of silicon. So they're arguing that to match these properties for the outer core, you can't put that much silicon in the core. However, if the Earth were made out of a C1 composition, we'd need a lot more silicon in the core. We'd need something on the order of 7 weight% silicon. And this tendency seems to be sort of relatively stationary. If we look at sort of like recent studies, people really are arguing for lower and lower amounts of silicon in the outer core and more of a role, for example, for oxygen and hydrogen. So at least sort of currently, if we look at the current studies on this, the argument that all this missing silicon could be in the core doesn't seem to stand up when we look at recent studies. So the next place to look would be, if we can't put all this silicon in the core, can we put it into the Earth's lower mantle? Now, if we do experiments on the Earth's lower mantle, we find that it's made out of 3 minerals. It's made out of this mineral bridgemanite, mainly, and then with a little bit of iron magnesium oxide, and then something called calcium perovskite, or what is often called Dave Mauite now. So if the Earth is made out of if the Earth's lower mantle is made out of the same chemical composition as the upper mantle, then we would expect these proportions of minerals in the lower mantle. But it's not just the proportions of minerals, it's also the chemistry of these minerals, which is also important. We have to take into account that not only would the proportions change if the chemistry changes, but the way that elements partition would also change. So bridgmanite is the most dominant mineral in the Earth. It makes up, as I say, most of the lower mantle, which makes up most of the Earth. Although we never see it at the Earth's surface, we can only make it in high pressure and temperature experiments. So if the lower mantle were to have a different composition from the upper mantle, then the first thing that would happen, if it was more silica-rich, then it would have more of this bridgmanite mineral inside it. And we would expect that, of course, to affect the seismic wave velocities in the lower mantle. So perhaps the study that made the best consistent argument for the lower mantle having a different composition was this study by Murakami, where they argued that the lower mantle may contain 90 volume% bridgmanite, which is a lot more than if the lower mantle had the same composition as the upper mantle. So the first thing that we need to do is measure the speed of seismic waves through minerals at the pressures and temperatures of the mantle. And the first thing we have to do is synthesize these minerals, and then we put them into a diamond anvil cell. So this is now looking through the diamonds of a diamond anvil cell at the sample. So these two samples of bridgmanite here are just about 80 microns across, and we're looking through the diamonds, and here's the gasket. And what we do to measure the seismic wave velocities, we do it as we do with lots of things in the diamond cell. We use lasers. So we shine a laser through these samples, and that interacts with what's called the phonons, the vibrations, the natural vibrations inside the mineral, and those vibrations have seismic velocities. So, and what happens is that we shine the Brion laser and it gets scattered, and in the scattered light it takes on a small Doppler shift, and from that Doppler shift we can determine the VP and the VS at the pressure and also the temperature at which we're doing that experiment. So when we can also measure using X-rays the density of those minerals at pressure and temperature, and then now we can also illuminate it with a CO2 laser, so a second laser, to actually heat it to mantle pressures and temperatures. So, and this is how that experiment looks like. So this is here's the diamond cell sitting in the middle here, and here's the optics for the Brion laser, and there's the optics that would be collecting the scattered laser light, which of course you can't see. And here is the optics for the CO2 laser, which of course operates in the IR, and so you can't actually see the CO2 laser, not that it's actually on, to be honest. But here, if we look through the diamonds in the microscope, you can see the two samples, and that's what happens when we illuminate with the laser. We can then heat the sample up and then simultaneously collect the VP and the VS of those minerals. So we've done a lot of measurements like this. This is just showing some measurements we did for magnesium silicon perovskite, for bridgmanite. So we measure the P wave velocity and the S wave velocities at high pressures. But if we really want to look at the chemistry of the lower mantle, then we can't just consider these minerals, this bridgmanite and ferropericlase, in isolation. We have to recognize that they have variability in chemistry. So what we do is we break down those two minerals into their individual end members, into their individual components. And then, of course, you have to do a lot of experiments to see how changing those components actually changes the seismic wave velocities of those minerals. And what you can see here is as a function of pressure. So here are the shear wave velocities, and then I'm just plotting the end member components in bridgmanite and in the ferropericlase. And what you can see is that they're all different. So if we imagine calculating what the VS is for this, what the shear wave velocity would be for this assemblage, it really depends on the chemistry because the velocities vary. So this is the FeO component of ferropericlase, and it has the lowest shear wave velocity. So then what we have to recognize, if the lower mantle has the same composition as the upper mantle, then it would not only have a certain proportion of these minerals, but it has certain proportions of the components. So when we try and put this all together into a thermodynamic model that then can explain for a given bulk composition what the Vs and Vp would be as a function of pressure and temperature. Now, if you notice here, if we had a different composition, if the lower mantle was made out of a C1 composition, for example, then the amount of bridgemanite would change, but the partitioning of iron would also change, and we end up with a little bit more FeO in the ferropericles. So now we have this data, we can compare it with the lower mantle, we can test and see whether the lower mantle, the velocities that we calculate really do match. And I do this calculation at about 1,000 kilometers, and I do that to try and avoid what's called an ion spin transition in ferropericles, because I think we don't really have enough data to make a reliable comparison at any higher conditions. So what you see here I'm plotting the shear wave velocity. Of course, I could plot the Vp and density, but it basically shows the same story. And here are the seismic reference models. So they don't all agree with one another perfectly, but they're basically within the same range in the mantle. And here I've plotted a range of bulk silicate earth compositions. And this includes compositions which are the same as the upper mantle, basically. And what you see is that we match seismic wave velocities for the lower mantle perfectly, they're in perfect agreement. This is a xenolith composition that has a slightly higher iron concentration. So you can see that if we raise the iron concentration of the lower mantle, it would be pretty sensitive to that. But I have to be honest, always good to be honest, we have some uncertainties on our measurements still, and we have uncertainties on the way that we still have to extrapolate certain end members. And this is probably a reflection of what our uncertainties are, which I've just put on the seismic velocities themselves. So even though this looks different, probably within our uncertainties, we wouldn't be able to tell the difference between these two compositions. So, but what this shows is that if we take a bulk composition from the upper mantle, we put it into the lower mantle, it matches seismic wave velocities, so therefore the lower mantle has the same composition as the upper mantle. And if I just stop there, then everything would be very good. We publish our paper and we say, yep, the lower mantle is the same as the upper mantle, and we all go home, we're all happy. However, now let's imagine that the lower mantle is made out of something else. Let's imagine that it's made out of a C1 chondrite composition. Basically, if we have a more silica-rich composition, we have a C1 chondrite lower mantle, we have more bridgemanite in the lower mantle, but because of a rather annoying twist in the partitioning of iron into ferropericles, it also lowers and counteracts the effect of having more bridgemanite. So basically, within the uncertainties, we can't really tell the difference between a lower mantle made out of the same as the upper mantle or a lower mantle made out of a meteorite composition. And this is actually the same if we take this composition, which is what you need to make the lower mantle out of, if the bulk earth has a C1 composition and that we then have a more magnesium-rich upper mantle. So this is then the composite reservoir for our upper mantle. And you can see maybe one day in the future we'd be able to get our uncertainties down. But for the time being, basically we can't tell the difference. And here's an ordinary chondrite, and it's not until you get to an enstatite chondrite that we get even close to being able to argue that the lower mantle is made of something different. So here we have no longer any ferropericles, and we can say for sure that the lower mantle is not made of an enstatite chondrite composition. Now, of course, this isn't where we wanted to end up, but at least I feel that I'm breaking the monotony of saying, well, there were some observations, and we did some experiments, and we explained everything. Because in the end, what you see is that seismic velocities, at the moment at least, we can't uniquely resolve the lower mantle composition. And of course, this is pretty disappointing, but it is still the state of things. And I still think it's important that we talk about these types of things, even if they don't come to these big happy endings that we really want. So we can certainly exclude possibilities that the iron concentration of the lower mantle is so high, and like I say, it's certainly not made of enstatite chondrite, which for me is a partial win. But in the end, we can probably go to much higher pressures, and then maybe the ferropericles effect doesn't work, but we have to do more experiments to do that, which is usually the end of most talks, isn't it? When you say, yeah, we still need to do some experiments. But in the end, I guess the fact of the matter is that the Earth is very effective at hiding its secrets. And I suspect that's not actually something which is limited just to my field. So now, let's talk about Mars, where the uncertainties, the observational uncertainties are smaller and the experiments are much easier. Okay, so neither of those things is true. So as I said, that Mars is very interesting because it may be a planetary embryo. It may tell us about an earlier stage in planet formation, and maybe one of the large impactors that hit the Earth had a composition similar to Mars. And what's interesting there is to know what would be the Martian core composition, because that material may have been delivered to the Earth's core, and it's otherwise difficult to resolve maybe what the composition of the Earth's core is, because we just don't have enough observations. But we still don't have enough observations even for Mars. There's plenty of potential light elements that might be in the Martian core. And we can only, by making some reasonable assumptions, we can only really discount silicon, because Mars is more oxidized. We don't expect silicon to have gone into the Martian core. There could be some oxygen in the Martian core, but that normally only happens if core formation was at quite high temperatures. You would need quite high temperatures to get oxygen into the core. However, there could be sulfur, there could be some high carbon and hydrogen, but all these elements, they are all volatile elements. And we know that volatile elements are depleted to an extent in terrestrial planets, and that depletion normally is considered to follow a trend of volatility as a function of the condensation temperature of those elements. So if we just try to make an assessment of how much sulfur there might be in the Martian core, we can do that by just assuming that Mars might also be made of different meteorites. So let's imagine that we made Mars out of a C1 chondrite. Of course, that's very volatile rich, and we assume it hasn't lost any volatiles. Then the Martian core, if all the sulfur went into the core, we could have a core with about 25 weight% sulfur. But that's not very likely, because as I say, if we look at elements which are similarly volatile to sulfur, we know that they are depleted in Martian rocks as a result of volatile processes during condensation and accretion. If we look at an ordinary chondrites, for example, so people often argue that ordinary chondrites are what Mars might have been made out of, then if we made Mars from an ordinary chondrite, you'd have 10 weight% sulfur in the Martian core. But if we really look at the depletions of volatile elements, like Yoshizaki and McDonough did, they correlated how much of those volatile elements have really been lost from Martian rocks. And by looking at similar elements that didn't end up going into the core, they argued that you shouldn't really expect much more than about 7 weight% sulfur in the Martian core. And if you do the same calculation for the Earth, you'd argue that there shouldn't be more than 2 weight% sulfur in the Earth's core. So when we can do the same thing with carbon, and what you see is if we do the same thing with carbon in meteorites, we see that there should be much less carbon available. And carbon is more volatile, than it has a lower condensation temperature, so we would expect there to be less carbon in the Martian core, and I would argue by the same argument that there should be even less hydrogen. So it really seems like sulfur looks like the most likely element to be in the Martian core. But now let's look at the observations that we get from InSight, which has already landed. Okay. So InSight landed on Mars in 2018, and after the first year, from the data that was collected in the first year, there were S waves identified that had bounced off a liquid outer Martian core. So InSight collected in the first year a couple of signals as a result of Mars quakes, which had produced seismic waves and bounced off a liquid outer core. And by looking at the core radius that they could calculate from these measurements, core radius is 1,830 kilometers. That was a bit bigger than what people expected it to be. And if you combine that radius with measurements of the moment of inertia and the density of Mars, then you could come up with a measurement of the density of the Martian core. So when you get a density which is significantly less dense than pure iron, right? So even more so than what we find on the Earth. So it really looks like there's a lot of light elements dissolved in the Martian core. Now, a little later, there were several events that were identified almost on the other side of Mars, and these had transited through the Martian core. And these were quite interesting, actually. It's a nice story, because this event wasn't a Mars quake per se, it was an impact. And because the Mars Reconnaissance Orbiter was still in orbit taking photographs of the Martian surface, it was possible to get before and after images of this impact, which created this event, which created the seismic waves that traveled through the Earth and arrived at InSight. And that's really useful information because it provides very precise location information. And that's really important for InSight because normally you get location information by assessing the measurements from lots of different seismometers, but actually there's only one seismometer and that's just InSight. So this was very useful information, and they could use it to determine the P wave velocity, make an assessment of the P wave velocity through the Martian core, which is actually pretty cool. And when you look at that P wave velocity, it's actually pretty similar to pure liquid iron. So whatever we expect for this light element that's in the Martian core, we can see that it lowers the density by a lot, but it doesn't actually affect the P wave velocity very much. So now what we need to do is measure velocities, P wave velocity and density for compositions that may be Martian core compositions. And that's actually, it is pretty challenging to measure these things for liquids. Measuring the density of a liquid, for example, is very tricky. It's not like solids. We just measure the lattice reflections. When we have a liquid, that's much harder. It's much harder to keep liquids inside experiments because they have a tendency to go where they want to go. And we do this inside, so we make P wave velocity measurements using a multi-anvil. So a multi-anvil is a very big press that presses down and compresses a set of 8 tungsten carbide cubes. So these cubes are made out of tungsten carbide. They're very hard. They transfer the pressures very effectively. So in the multi-anvil, these are about 32 millimeters in length. And then we have a little transducer on the back of one of these cubes, and it sends a little P wave. Okay, so I'm sure a seismologist probably wouldn't like that because the frequency of our P waves are in the ultrasonic range, and seismologists don't like to hear that sort of thing, but I'm going to call it a P wave, okay? So when that P wave travels through the anvil, it travels through a little buffer rod, and then it travels into the sample, and of course we melt the sample in the furnace. So the furnace is at very high temperature to melt that liquid, and hopefully the liquid doesn't escape. Eventually they always escape. And if we look in detail, it looks like this. So this is the arrivals that we get back at the transducer. And so it happens like this. We send a little P wave. It travels through the anvil. It travels through the buffer rod, through the sample. And every time the P wave travels from one type of material to another, it sends a little reflection. Look, there's a reflection from the front of the sample. There's a reflection from the back. And all of those little returning reflections are recorded by the transducer. And that way we can measure the travel time for a P wave through that liquid. And then if we go to the synchrotron, we can shine X-rays into the sample, and we can get an X-ray radiographic image of that molten liquid sample. And that way we can determine the length of the sample. And so from the travel time, we then measure the time through the sample. We combine that with the length, so then we get the velocity of these P waves through the sample at pressure and temperature. And then, of course, we can start with looking at iron, and then we can add some sulfur, then we can add some oxygen and add lots of different compositions. And that's what it looks like when we recover the whole thing. So that's a section made after the whole experiment. And you can see here's our furnace. It's made of boron-doped diamond so that we can get all the X-rays through it. And that was the quenched sample, which of course then we can analyze and make sure it had the composition we thought it was going to have. So if you want to measure the density of a liquid, then the best way to really do this is using the X-ray absorption method. So if we have an X-ray just like light going through samples, if we use the Beer-Lambert law, if we have X-rays, then the attenuation of the X-rays, the absorption, if you like, of the X-rays is a function of the density. So we do this again in a multi-amble. We have a capsule that we keep the sample in, and then we scan the whole press through the X-ray beam. And as you do that, then you absorb, then the absorption from your X-ray beam goes down as it's going through this ion-dominated liquid. And if we look at the material before and after, we can then normalize out the path length absorption of the X-rays and get an estimate of the absorption purely from the iron metal sample. And we put that through the Beer-Lambert equation. But what's actually quite important then is to be able to measure the path length. So again, we can use another type of equipment. It's called a Paris-Edinburgh cell. And with a Paris-Edinburgh cell, we rotate it inside the X-ray beam, and we can get a three-dimensional image of the liquid. And so that gives us the shape of the material through which the X-rays are passing and being absorbed. So I put all these types of measurements together into a thermodynamic model. That's what we do in the end. Make a model, explains everything. So with our thermodynamic model, we base it on these end members, so with an ion, an FES, and an FeO end member. And I support this model not just with these measurements that we do, because as you'll see in a minute, the uncertainties on these measurements are quite large. So we try and support them with other types of observations. And you can take, that's the nice thing about thermodynamics, is that the types of parameters like the volume appears in multiple situations in thermodynamic calculations. And one of the situations, for example, where the volume or the density of FES appears is when you melt FES. So if we measure the melting curve of FES, if we go from the solid to the liquid, we measure the pressure and temperature at which it melts, and if we know the equation of state of this solid material, we can actually get a good constraint on the volume of the liquid from the melting curve. And we can combine that volume into a thermodynamic model that also contains our density and VP data. And when we mix iron with sulfur to get iron-sulfur liquids, we can also get information from looking at the iron-sulfur phase diagram. So if we measure this phase diagram as a function of pressure, it gives us an indication of something called the excess volume of mixing. So that's the non-ideality of mixing, of when we mix these two components to get the density, how the density changes through the mixture. And this is particularly important when we try to look at oxygen, because we really don't have, so it's not so easy to study oxygen in terms of its VP and density. So that's just showing how our model then matches our actual experimental observations. And you can see that the errors on these density measurements are very large, but we believe our model is more constrained because it involves these phase equilibria calculations that tend to pin down the volume very effectively. So now we can look at the effect of sulfur and p-wave velocity at the top of the Martian core, right? So here's density, and here's, as we add sulfur to pure liquid iron, this is how it affects the density of that liquid. So this would be pure iron liquid, and I've calculated this for several different temperatures. You see the temperature doesn't really make much difference, but what you see is to match this density estimate from Stehle et al., you would need about 30 weight% sulfur in the Martian core. And that's pretty unrealistic. That's even more than you would need if the Mars was made out of a C1 chondrite. It would basically mean that you accreted this planet without any loss of volatiles, and we know from Martian rocks that there are losses in volatile elements due to accretion and condensation processes. Not only that, but if we look at this, at how much sulfur we would need to add to match the density, that amount wouldn't actually match the VP, the P wave velocity that we get for the Martian core. But this is where the story starts to get twisty. And we introduce the first level of what I would call interpretive uncertainty. So faced with this, this situation, that it didn't matter how many volatile elements you were prepared to put into the Martian core, you couldn't actually match the density. Even if you put all the sulfur from C1 and all the carbon and even a lot of hydrogen, it would be very difficult to match that density. Two studies proposed a reinterpretation of the seismic observations. So, and they recognized a new arrival that actually came from this impact event, from an arrival that they argue grazed the core mantle boundary. And they argue that there's another layer there, this time a silicate melt layer. And that the original observations of this bouncing S shear wave were actually bouncing not off the core, but bouncing off what we might call a basal magma layer. And this then, if this is really the case, and I would remind you that this is based pretty much on one arrival that InSight measured, then this reduces, this layer, they argue, is about 150 kilometers, and it reduces the core radius then to only 1,670 kilometers, which of course then allows the density, the calculated density, to be higher. So now it looks like there's fewer light elements in the Martian core. Now what you have to sort of appreciate here is that if we interpret this, we are interpreting something which is not based on a whole lot of measurements. And we're building something which is probably akin to a house of cards in many instances. But as far as I'm aware, InSight doesn't produce any seismic data anymore. There are no plans for another seismometer to be landed on the surface of Mars. So this is what we have. This is what we get, probably now, for a very long time. And people are going to argue over this, I can imagine, lots and lots. But let's just see how this affects our considerations of what the core might be made out of. So then if we lower the density, we raise the density rather, with this new assessment for the Martian density, then we have a sulfur concentration which is still pretty high. Yeah? Although the density is then much higher, it would still require, if sulfur is the only light element in the core, then it would still require something like about 20 weight% sulfur, which is still much, much higher than people would argue based on cosmochemical arguments of the volatility of sulfur. There shouldn't really be that much sulfur. But then when we thought about this, so this is the model that's being proposed, that there's an outer core, a liquid outer core, then there's a basal magma layer, and then there's the mantle. And this basal magma layer sits at the bottom of the mantle, and of course the main way that you might have a layer there, certainly at the proposed temperatures, is that it would have to have a lot of FeO, a lot of iron oxide inside it. So iron oxide would lower the melting temperature, and of course, it would keep this layer there because it would make it very dense. So if you had a basal magma layer rich in FeO, it raises this question, what would then be the oxygen concentration of the core? Because the oxygen concentration of core is dependent on a few things. It's dependent actually on the temperature, right? So the higher temperature, the more oxygen we get. It would depend on the iron oxide concentration of the material that it was in equilibrium with. If we had a very high FeO concentration in that material, you would partition more and more oxygen into the core. And this is actually something that we can calculate. We have the phase relations, we have the experiments to be able to calculate how much oxygen then you might expect to have in the core. And we were thinking about doing that, and even before we'd formulated the idea in our mind, the next paper came out. It's very rapid. It's hard to sort of like keep up, you know. You're going down to the lab, somebody tells you they've discovered an inner core on Mars, you turn around and go back to your office. So Bai et al. Did just that. So they consider that they have identified two very weak arrivals, and one of them they believe is an inner core transiting phase, and another one that appears to be a wave which has bounced off an inner core. And what was then very interesting about this was that they weren't proposing that and they have an estimate for the density, and they weren't proposing that this estimate of density matched iron metal or iron sulfur, but it actually in fact matches iron oxide. So they argue that this is an evidence for an iron oxide inner core. And of course, that for me is very nice, because for once we would have an observation that would reduce the uncertainties. It would provide us with a constraint. Because if we have a solid FeO inner core, then it's quite straightforward to calculate the oxygen concentration in the outer core. And that's what I've done here. So I've calculated how much sulfur would be in the as a function of the sulfur concentration, I've calculated how much oxygen would be in the outer core if it's in equilibrium with an FeO inner core. So if we make the core out of FeO, this is how much oxygen you could have. And of course, it's a function of sulfur, but if we then put this together with density and Vp, you get the idea that we can then find a solution. But what's kind of interesting about that is that if you did have an FeO saturated outer core, there would be a tendency for it to react with the mantle and partition FeO into the mantle. It would react with mantle rocks to make an FeO-rich layer. So there's another aspect which is really intriguing. It could be that if there is an FeO inner core, that a sort of an FeO-rich basal magma ocean may be inevitable. It may be the sorts of things that have to actually go together, which would then be very intriguing, because it would start to stabilize this otherwise house of cards. So then, of course, what I did then is I made that calculation for an oxygen-bearing liquid, and you can see that with about 10% sulfur in the core now, we can match the density very easily with about 6.5% FeO. And FeO, the oxygen concentration, actually raises Vp, so it actually makes it very easy then to match the P-wave velocity. So if we put this, and then if we imagine, or we consider, for example, that there may be a little bit of carbon, one could imagine that you could bring the density down, and it would then originally match these estimates made by Yoshizaka and McDonough for what you'd expect to be in the core if based on volatile elements. So, if I'm going to conclude here, so sulfur alone doesn't seem to match these observations, but if we had an FeO inner core, which is what the seismology seems to sort of be arguing for, it may actually be consistent with having an FeO layer there, and that would allow you to put sulfur and oxygen in the core, and it would match those observations. And I would just say this one last thing about why this is kind of interesting, because if that is really the case, then we can make an estimate for the temperatures required to accrete Mars. Because to get that oxygen into the core to begin with, we would have to have relatively high temperatures of accretion, and we can actually calculate those. And what you get is that you would need an average temperature of formation for Mars of 3,000 Kelvin. And I think that's quite an interesting constraint on a planetary formation process. However, the remaining uncertainty lies not really anymore in the thermodynamics, but in this seismic interpretation. And I have a great fear that this is not going to change. This is what we have right now. It's going to be raked over and argued over for the next, I don't know how many years, until somebody puts another flipping seismometer back on Mars. Thanks very much. Okay.
Thank you, Dan, for an amazing talk. There is time for a few questions, and if you have any questions, please go to the microphone. I have a question.
Okay.
No, actually, I have two questions.
Righto.
How representative are your experiments? They're tiny, 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 and maybe even more tiny than what I could describe. how representative are they from the composition you're trying to measure?
Are you saying because the Martian core is very, very big,
No.
and our samples are very tiny, that there may be a problem there? Yeah. I mean, of course, one of the issues in that respect. I mean, of course, if we measure the density of that material, you know, the size of it, it really creates uncertainties, of course, because when it's very, very small, it means that when we go to the synchrotron, we need to measure the length of it very precisely, and that, of course, introduces the main uncertainty. So another aspect, of course, is that we're actually measuring this. We're not measuring these velocities at seismic frequencies. We couldn't do that because the wave lengths would be far too large. So we have to measure it at ultrasonic frequencies. But from what I understand about anelastic responses in liquids, this shouldn't be a problem. So of course I'm going to say it's no problem whatsoever.
Go ahead.
Okay. Hi, great talk, thank you. Molly Anderson from University of Florida. And I was just wondering if you have considered nitrogen as the light element for Earth specifically. Just from my understanding, there's a pretty major control that nitrogen could have over these seismic velocities. So I was just wondering if there's a reason that it's not considered here, or what your take is on that.
Yeah, so if you know, generally when we think about what the light element in the core could be, we think about the availability. And quite often in that availability, we look at the likelihood of whether these elements are going to have been lost through volatile processes. Okay. So in general, you know, if we look at other elements that we know didn't go into the core, we make assessments and we know that they are depleted in the Earth as a result of as volatility and volatile processes. And nitrogen, we believe, is strongly depleted. There shouldn't be enough nitrogen. But of course, there are other ways of making planets. You know, if we accreted the Earth, for example, in a solar nebula atmosphere, then all those bets are off. But that's generally not how we think that the Earth was accreted. So nitrogen, we generally consider that there isn't cosmochemically, there shouldn't really be enough nitrogen to account for at least the light element in the Earth's core. There's almost certainly some there.
Yeah, okay, thank you, I appreciate it.
Thank you so much. You talk about moment of inertia when Mars had one layer core, but like what happened that now we think Mars had like 3 core layers? Like how moment of inertia will help us with that?
Yeah, I mean, okay, when they put that in the moment of inertia calculations, of course they do. That's one of the things that they look at a lot, you know, to match the moment of inertia, you know. But of course, the moment of inertia it's not that accurate. It gives you an idea, and you can put these layers in without manipulating the moment of inertia, especially if you adjust densities of other competing layers. So it's kind of apparently. So Amir Khan tells me it fits within those sort of observations. They do take that always into account.
Awesome.
You know?
Awesome, thank you.
Hi, and thank you for that really wonderful talk. I wonder if you can say anything about the complexities of any potential re-equilibration within the planet after core formation.
Yeah. So the idea would be that you formed Mars at a significantly high temperature, and then you would put enough oxygen into the core. And then as Mars cools down, the solubility of oxygen into the core would tend to go down, and then because you would reach the solubility limit, you would start to precipitate iron oxide. Now the question really is, because that's not it's not really like a melting temperature like on Earth, it's really a solubility sort of like limit, and it will change as we go from the core mantle boundary up to the inner core boundary. So what's really interesting to investigate, when I did sort of like initial calculations on this, I saw that actually the solubility seems to go, let me say, down with pressure. So what that means is that you can be in equilibrium with FeO at the core, but actually undersaturated at the top. And that's really good, but it seems close. So that means that liquid wouldn't precipitate FeO at the top of the core, but it could react with the mantle, and as we say in thermodynamics, because that mantle would then lower the activity of FeO, you could create then a growing FeO layer, because it's not in equilibrium with pure FeO, but it would be in equilibrium with an FeO-bearing mixture. And as I say, that might be actually internally consistent. It might be inevitable. If you have an inner core, then you would make that reaction. And then slowly what would happen is you would sort of precipitate more and more FeO into that layer. And I guess probably it might not be in equilibrium with the rest of Mars. So then you'd have to diffuse out FeO-rich material into the rest of the mantle of Mars. But at those temperatures, diffusivity is slow, and the liquids are very dense. So I don't know, until somebody does some calculations, I don't see any reason why it can't sort of stay like that,
Awesome. No, thank you very much.
Yeah. Do you think there is any parallel between the basal melt layer on Mars and the D double prime on Earth?
Yeah, it's interesting, isn't it? Because you could, in principle, of course, you could argue the same thing for the Earth, that we have oxygen in the Earth's core, and that as oxygen starts to precipitate, you could have a reaction layer. But when I've done sort of similar calculations for the Earth and how much oxygen you would have in the Earth, it's actually the other way around. There isn't enough oxygen then, because assuming that we know what the sulfur concentration is, to actually saturate at the core mantle boundary. So it would potentially go the other way.
Hi Dan, Razman Karakas, IPGP. I was wondering, why do you so stubbornly want to put sulfur in the core? Why not carbon or hydrogen or silicon? I mean, we have an n-dimensional space.
I know. Because I'm always looking for the constraints, right? And the constraints we get from looking at mantle rocks, for example, and we have a volatility trend. And that volatility trend is a function of the condensation temperature. And if we look at elements which are similar to sulfur, but not siderophile, right? We know that the Earth, for example, and Mars is depleted in those elements. So if we take that sort of like that depletion just due to volatility, and then we look at how much sulfur is then missing, we can make an estimate of how much sulfur should be there. And that's a kind of a cosmochemical estimate based on the argument that elements with similar condensation temperatures behaved similarly during condensation and accretion. Well, if we follow that condensation temperature down, and when we get to carbon and hydrogen, then those elements should be much more depleted. And it's not like we don't see that in meteorites. If we look at carbon, for example, even in the other meteorites, we see that it is much more strongly depleted. So my argument there is based on the likely cosmochemical abundance based on volatility. But what flips this on its head is if we think about models where the Earth might have accreted and been in a very hot stage in the solar nebula still. So if we built a solar nebula atmosphere while the Earth was still sort of accreting, and that has to be a very early Earth, while the nebular gas is still there, then you could in principle partition hydrogen or other volatiles into the magma ocean and into the core. And of course, that's a possibility that we should that we now has to be taken into consideration. My feeling is I don't like it because it removes that constraint of the lack of volatile elements from the Earth that we generally see in the depletion of volatile elements, but it's certainly something that we have to keep in mind.
Thank you.
Well, you did say that would be the last question, so... Thank you.
If you want to hear more about this, Dan is giving another talk this afternoon. So
in the Bernie Wood session, please come to the session in honor of Bernie Wood. He'd be very pleased to see you all there.
Thank you, Dan, for this very good talk. And thank you, everyone, for showing up. We have one more plenary tomorrow. And keep coming. It's really nice to see all of you here. Thank you. Have a good lunch.
Chers invités, veuillez vous diriger vers votre salle d'atelier. La présentation débute maintenant.
Dear guests, please proceed to your breakout room. The presentation begins now.